Welcome, AP students. I trust you are doing well. Today, I want to talk a little bit about a quick outlook over the next few days I'd like to do. You look at this assignment that I have up here, this PowerPoint that I'm going through. This problem right here was the one that I had assigned you for a bell work. And everyone knocked it out of the park. So I'm not going to take the time on this video lesson to break it down. You guys got it. You know it. You know how to do it. I'm really happy to see that. But we're going to wrap up. I will have posted at some point tomorrow a virtual lesson for Unit 2 review. And if you look in RenWeb, you'll see that I have another AP Classroom review due Friday at 11:59 p.m. I'll have that uploaded tomorrow as well. So you'll have the next couple days to work on that. I also have some 5 steps to a 5 work for you. I do realize the answers are there, but I still want you to try and work through those problems. Please be diligent about doing that. It'll be very helpful for you. You probably already seen my email and you understand that they change it. You are going to do your AP exam from home with a lockdown browser and you have 45 minutes to complete it. It is a all free response test, all free response test. So that's what my bell work is going to basically consist of. Tomorrow's bell work will be the same thing. And if there's issues with them, I will break them down for you and show you them. What I'm planning to do is over the weekend, I'm going to make another video, virtual lesson, and it'll be over chapter, or I should say Unit 3. You'll have Monday, Tuesday, Wednesday to complete those components. And my plan is Thursday, we're going to have a test. I will place that test in Moodle, and it'll be a 50-point test in Moodle, and it's going to cover Chapter 1, Unit 1, Unit 2, and Unit 3. So you'll see it in next week's lesson plan, but I wanted to touch base with you guys on that. So next Thursday, 1 week from this Thursday, it'll be right before our Good Friday break and our Easter break. Because what I want to do is I want to get through all 7. It's 7 sections. 8 and 9 are canceled, so we're not going to worry about those. But I want to get through all these sections so that you are refreshed and able to go. Obviously, running through number 3, Unit 3, Unit 4, 5, 6, 7, I'm not going to be able to run through as quickly. So it's going to take a little bit more time. So it'll probably be a week apiece, maybe a little less than that, so that I can get this all done by the 1st of May, because your test is going to be really close right after that. I'm not sure when the school is going to ask that to be done. I will keep you posted on that. All right, so let's jump into this little tutorial here and get through this. This was the bell work. Once again, you guys truly understood what to do. You take the mass here and the mass here. You have a sample that was right at this particular mass, and we knew the carbon all came from the sample in burning. The carbon and the hydrogen all came from this hydrocarbon. You didn't know how much oxygen because you were burning it in oxygen. So you took the molar mass of carbon dioxide, went to moles, then you multiplied that. 1 mole has 12.01 grams of carbon. You got that number. You did the same thing here with your water, and then you took and added them together and subtracted them from this 4.36 gram, and that gave you your oxygen. Once you had this mass, you convert them to moles divided by the smallest mole. That gave you your empirical formula. You had your molar mass given to you, so you take the molar mass divided by the empirical molar mass, and then you multiply your empirical formula. It'll give you a small whole number. In this case, it was 2. multiplied it out, and everyone got it. So I'm really happy with that. So good job. So here's a little bit of a different example. Pretty straightforward. We're going to break this down here real quick. In a given sample of a hydrocarbon, it was found that 92.24% of it was carbon. So anytime you deal with this type of a problem, it could be a little bit more complicated than this, but it's giving you a percent. You automatically assume you have 100 grams. This says a hydrocarbon, so all I have is carbon and hydrogen. That's it. That's all this is. So if I change this to a mass, so I have 100 grams, I have 92.24 grams of carbon. And I'm going to convert that right away to moles. A mole of carbon is 12.01 grams carbon. So if I do that, I have 92.24 divided by 12.01, and I have here 7.680 moles of carbon. So I had 4 sig figs. So now I can simply right away, it's 100 grams. I can just minus that off. I got 100 grams minus my 92.24, and that's going to give me 7.760. So 7.760 grams of hydrogen. I'm going to go right to moles immediately. So 1 mole hydrogen, 1.01 grams hydrogen. So if I plug that in, you can see pretty quickly what's going to happen here. 7.760 divided by 1.01. I'm going to have 3 sig figs, 68 mole of hydrogen. You see right away, you take the smallest mole total and they're both the same here. So my empirical formula is CH. So that's how you would do this type of problem. Now, you could have been given oxygen might have been in there or something else. You do it the exact same way. All right. So we're going to have a few justifications here. I want to just talk and make sure we fully understand all those things. Which species has a smaller radius? So this comes back to periodic trends. So looking at our periodic table, we have chlorine, and we have chlorine with a 1- charge. So we have the neutral chlorine and the anion chloride. So remember the trends in justifying this. You would have to say something along the lines like this. You have added an electron. So by adding that electron, you have now caused that radius to increase. So the smaller radius would be the neutral chlorine. By adding the electron, you now have caused the atom to expand. You added electron, so now its charges are going to be more. There's more negative than positive, so it is going to expand it out. So the periodic trends say an anion is larger in radius than its neutral self. In this case, this is larger. You look at sodium and the sodium cation positive, it's the opposite because you're dealing with a metal versus a nonmetal. So the ion form of a nonmetal's radius is larger. The ion form of a metal is smaller. So sodium 1+ is going to be smaller than the sodium. Why? Think about that. It lost a layer. So sodium gave up that 3s1 electron, which means it's now going to be able to compact itself more. So when you talk about chlorine, you go Cl, you have something like that. You go Cl-, you're going to go larger. You have Na, do something like that. And then Na+. So that is the periodic trends when it deals with atomic radius. Electron configuration, please don't forget, I know this is really elementary at this point for you guys, but there are still questions that deal with this. So we ask anything about electron configuration, you get your periodic table out and you look at it. So if it says, give me the electron configuration for calcium, so we will just run right through this. We're going to go, we have 1s2, we have 2s2, we have 2p6, we have 3s2, we have 3p6, and we have 4s2. So that is our electron configuration. We could have wrote the kernel method, but a lot of times they don't want the kernel method. They want to see that you know fully how to write it. Now, we have the cation Ca2+. So remember what's going to happen. This is going to go away. So Ca2+ would be 1s2, 2s2, 2p6, 3s2, 3p6. And 3p6 is going to give you argon's configuration. So it'll be configured like the noble gas argon. So now we have phosphorus. So we'll deal with a metal, now a non-metal. Remember, they are different. So if we look at phosphorus here, we have 15 electrons. So we have 1s2, 2s2, 2p6, 3s2, 3p3, 3p3. Now when we get the negative charge, remember it's going to become larger because it's gaining. So now we would have to write this out as 1s2, 2s2, 2p6, 3s2, 3p6 now. And we already have the p3 minus there. You'd have to have that to designate that that is not argon. It's actually phosphorus as a 3 minus charge. So that's electron configuration. Once again, this is just wrapping up all the loose ends of Unit 1. So let's look at this here. Why is the first ionization energy of potassium less than the first ionization energy of bromine? So let's look at where they are here. So they are both in the fourth energy level. You have potassium, you have 19 protons, and if you come down here across to bromine, you have 35 protons. So why is the ionization energy less? So think about this. So the trend is, this is the same, this is the fourth energy level, both of them. As you move across, there's less shielding. So now it's going to become more compact. There are more positive units. The overall nuclear charge is greater. Yes, there are more electrons. This has 35 electrons to 19 on potassium. However, they are in the same layer. So 35 protons is going to compact it. So here you have a size, something like maybe this. You come all the way over here, you have a size like that, so significantly smaller. So the overall nuclear charge is stronger. Coulombic law, this is a justification you could use on this. Coulombic law states that the distance apart and the strength of the nuclear charge is pulling them tighter and closer together, so therefore it has a stronger attraction on them electrons, and to remove one would be much more energy than on a potassium, where there's only 19 protons, so the overall nuclear charge is less, and its outer electron is further out, so the distance, the radius, the distance away is greater, so therefore the Coulombic force is less. So that's why the ionization energy is less for potassium than it is for bromine. And that would be your justification for a question like that. All right, so here's a question. Removing a single electron from which of the following elements would require the most energy? So here we have potassium. Potassium is in our first period here, our first family group, our alkali metals. So we have rubidium. It's in the same family. So here you have size. So let's kind of just do a quick comparison of size. So as you go down a group, they get larger. So we would say something like this. We go down because rubidium is directly under, so it's going to be a little larger. And then we have all the way across to bromine is in the same group as, the same period as potassium. So bromine is going to be a little smaller, and then you have iodine, which is directly under bromine, still on the far right, which means it's going to be smaller than the ones on the left. So we could automatically say required energy, these are metals, they tend to lose, so the ionization energy is going to be lower, so we cross those two off. Now we're going to look at between bromine and iodine. Iodine's directly under. As you go down, the radius increases, so iodine is going to be slightly bigger. So which one? Bromine. Bromine would have the most energy required to remove an electron. And that's the justification for that type of a problem. So here is another one. Predict the element from the following list that would have these ionization energies. So ionization energy is the energy required to remove an electron. And there's energy 1, energy 2, energy 3, energy 4, ionization energies as you look at different electrons. So let's look at this here. So first one we have here is 738 kilojoules per mole. Not a whole lot. That's going to be removed pretty quick. Here we have one that's not too much more than that. It's basically doubled. So that means 1451 kilojoules. That's going to be fairly easily removed. Now what happens here? You jump up 7 times, basically. 7 times. That's not going to be removed too easily right there. 10,000, nope. 13,000, nope. 17,000 under normal means that's not going to be removed. So when you look at this here, you're going to have 2 that are going to be removed. When you look at the list we have here, this is 1 will be gone from here, 2, 3, and silicone can act either way. It's a metalloid. So when you look at this, these 2 here will easily be removed. So that's going to tell you magnesium is this particular species that would have this take place. And that's how you look at an ionization energy chart and you determine which one would be removed. Now, if this number here was maybe around 3,000 kilojoules or possibly 4, that would therefore be aluminum. But when you look at this one being so much more than the 1,451 kilojoules, it's not going to be easily removed, and therefore that's magnesium. All right, so now let's look at this here. Which of the following is isoelectric? Isoelectronic. So we talked about this previously. Let's just take a look at here. So here we have chlorine, iodine, and fluorine. Notice that they have all 1- charges. Isoelectric doesn't mean that. It can be confusing to think that it means that. These are the same charge. They're in the same family. That's not isoelectric. So that's not it. So when we look at the next one, we have right there 3 noble gases. We have krypton, we have xenon, and we have radium. When we look at this, they are not it either. They are the same outer electrons, 8, but they're not isoelectronic. Isoelectronic means that they have the same noble gas configuration. So let's look at this last one here. So we have iodine, as a 1- charge, which means it's configured like xenon. We have xenon written there. And then it has barium. Well, barium, if you look at in the 6s2, it will lose both of those, fall back to the 5th energy level, and that's xenon. So when you talk about isoelectronic, here you go. Isoelectronic, the same electron configuration. So isoelectronic, same electron configuration. All right. Which has the lowest energy? This is a little tricky. Hopefully not for you. We've talked about this previously. You might look at it and say right away, oh, 3rd energy level, that's it. Well, remember what happens to D. D falls back, but D has high energy. So when you look at your periodic table, you see your 4th energy level. It goes 4s2 and drops back to 3d. That D has more energy than the actual 4p. So when you talk about this, and then you go to 4d, 4d is actually going to be higher energy than the 5p. So 4s, hopefully you followed me on that. The 4s in these 4 that are listed there, 4s has the lowest of the energies. Hopefully you followed me on that, because the S group is the lowest. When you go from 4s to 3d, the D has high energy, has higher energy than the 4p. Now the 4d there would be the highest of all of them if you talk about the highest energy level. So in this case here, lowest energy would be 4s. Which peak has the most energy in this particular element? So first off, let's even pick out what element we're talking about here. So when we look here, we don't see a graph, we don't see a y-axis. That's okay, you don't have to have that. You will have some charts that do not show this. This is a nice style of a free response question. Might ask you a few questions. For example, which peak has the most energy? Which element is this? Those are 2 questions that could be derived right from this. When you look at this, you have increasing megajoules per mole. That means going to the left, this direction here, you're getting close to the nucleus. So you're talking about the nucleus being like right there. So when you look at this, we could say this is 1s2, this is 2s2, this is 2p6, this is 3s2. We could say this here is 3p1. Since that's about half the size of that, and that's 2, that would mean that's 1. So if we look at this, we have aluminum. So we identified our element. Which has the most energy? Please don't let that trick you. You might want to say, oh, this peak right here. Or you might say, oh, this here because it's the tallest. That's not correct. The highest energy level is 3p1. So right here, E has the most energy. I know that sounds a little tricky. Please follow it through that logical thought process and you'll be okay. And ladies and gentlemen, that is it for Unit 1. So the last thing for Unit 1 is the 5 steps to a 5 questions I asked you to submit for 8 points, and I will be looking for those. And I know that, once again, I do realize that the answers are in the book right behind that pages that it's on, but I would like you to try those, work them out, make sure you understand that. I have high confidence that you will all pass this AP exam with flying colors and get 5s. That's my goal, and I know that's your goal as well. All right, so thank you for watching this tutorial. I'll have another one posted at some point in time tomorrow, which will cover Unit 2. Thank you. Go in peace.